Okay, now let's move to the second part. That is fine-grained image recognition. Um, okay, now I'm Xiu-Shen from Nanjing University in Technology. In the following, I will talk about fine-grained image recognition, especially in one specific learning paradigms. In my talk, I will firstly give a brief introduction of fine-grained image recognition. Then I will introduce three main aspects of the localization classification subnetwork learning paradigms of fine-grained recognition, as well as some other representative methods. In the previous talk by Serge, we see the differences distinguishing fine-grained image analysis from generic image analysis. As shown in this slide, the fine-grained recognition task is to classify different breeds of dogs. And compared with generic image recognition, fine-grained recognition is necessary to capture the subtle visual differences. For example, the discriminative features such as ears, noses, or tails. Also, characterizing such features is also desirable for other fine-grained image analysis tasks. For example, the fine-grained retrieval in the rest portion of this tutorial. Okay, in real applications, fine-grained recognition is widely used in diverse tasks of real world. For example, this is a competition held by the Nature Conservancy on cargo in 2016. The task of this competition is to detect and classify the species of fish from the images captured by the camera on ships. Apparently, it is a fine-grained recognition task. And in the next year, another competition held by the Nature Conservancy was announced in cargo. And this task required it to identify hopback whale based on the patterns of the whale's tails based on fine-grained techniques. Additionally, and as mentioned by Serge, the famous naturalist competitions in the fine-grained community ask participants to develop fine-grained algorithm to developing with not only fine-grained problems, but also the long-tail challenge. Regarding the long-tail recognition task, and Joshua and Bingy will talk about it later. And other real-life applications like to identify plant species and recognize car models or recognize fine-grained products or even recognize ship and aircraft models from remote sensing images. And as I've mentioned in the opening remarks, the small interclass variations and the large intraclass variations is a unique character of fine-grained visual analysis. It is also a major challenge of such an interesting problem. Thus, for handling such a challenge, a key of fine-grained visual analysis is to locate and capture the discriminative but subtle part-level patterns and features to describe fine-grained objects. For example, it is desirable to obtain the cues of the head colors and the wing textures of birds, okay? Because they can distinguish it from other subordinate categories. On the side of fine-grained recognition tasks, there are some benchmarks in the literature, and also some of them are mentioned by Serge. And the most popular use is a CUB, which is a bird species classification dataset. And in addition, other famous fine-grained dataset like Stanford Dogs, it contains 120 fine-grained classes and about 20,000 images. And for Oxford Flowers, it has 102 classes and 8,000 images of flowers. and the others are aircraft and cars and so on. Beyond those earlier benchmark datasets, in recent years, more challenging and practical fine-grained datasets have been proposed. For example, the nature list. It contains different species of plants and animals. And also our proposed RPC for retail products. And the novel properties of these datasets include the fact that they are large scale, have hierarchical structure, exhibit a domain gap, or form a long tail distribution. And these challenges also illustrates the practical requirements of fine-grained image analysis in the real world and motivate new interesting research challenges. And for fine-grained image recognition, it has been by far the most active research area of fine-grained visual analysis in the past decade. Researchers has attempted to deal with these challenges from diverse perspectives and gradually form the following three paradigms. And in my talk, I will elaborate the first one. In the learning paradigm of localization classification subnetworks, researchers have attempted to create models to capture the discriminative semantic parts of fine-grained objects, and then construct a mid-level representation corresponding to these parts for the final classification. More specifically, a localization subnetwork is designed for locating these key parts, and then the corresponding part level feature vectors are obtained. Also, the part level features are called the local level features or local level patterns. This is also usually combined with object level, global level image features for representing the fine-grained objects. In the following, I will introduce some representative existing methods in these paradigms, probably from four types. And the first one is to employ detection or segmentation techniques. And second is utilize deep filters. And the third one is leverage attention mechanisms and also some other famous or representative methods. For the first perspective, it is straightforward to employ detection or segmentation techniques. For example, the faster RCNN or fully convolutional neural network for segmentations. We can use this detection or segmentation method to locate key image regions corresponding to fine-grained object parts. Thanks to the localization information, that is means the part level bounding boxes or subtation masks, and the models can obtain more discriminative mid-level representations with respect to these fine-grained parts. Okay, now it could further enhance the learning capability of the classification subnetwork, and it will significantly boost the final recognition accuracy. And earlier works in this paradigm made use of additional dense part annotations, that is the key point supervisions to locate semantic key part of the objects. So that is why it is also called the strong supervisions in fine-grained recognition. And for example, regarding the early works, Bransons et al. Proposed to use groups of detected parts key points to compute multiple wrapped image regions, and further obtain the corresponding part level features by post-normalization. And in the same period, John et al. First generated the part level bounding boxes based on ground truth part annotations, and then trained a RCNN model to perform part detection. And in order to integrate both semantic part detection and abstraction, SPDA-CNN is designed uh, as a top-down method to first generate some part level proposals by interrogating the prior geometry constraints. So the geometry constraint will help the model to find the structural information. And then it uses a faster RCN to return the part level localization predictions. And these part level predictions are concatenated to form whole features to represent the fine-grained objects. And other approaches use segmentation information. One of the representative methods is our our mask CN. It employed segmentation models that is a fully convolution neural network to get parts and also the object mask to aid part and object localization. And we feed this object and part level ground truth mask because we just have the key point supervision. So we can generate a bounding box like supervision based on these key points. And we feed this ground truth as the ground truth of segmentation models. Then compared with detection techniques, the segmentation can result in more accurate part localization because the object of segmentation is in the pixel level. So the segmentation can return more accurate part localization. So we can use segmentation to return a more accurate the parts or object level masks, okay, like that. So furthermore, we use these objects or part level mask to select the useful descriptors and discard some noises or background descriptors. And it is very useful for the fine-grained recognition. However, employing the traditional detectors or segmentation models requires dense part annotations for training. It is labor intensive and would limit both scalability and practicality of the real world fine-grained applications. So it is desirable to accurately locate fine-grained parts by only using image level labels. So these set of approaches are referred to as weakly supervised, and they only use image level labels. So these methods are called the weakly supervised method in fine-grained recognition. Okay. It is very interesting to know that since 2016, there's an apparent trend in developing fine-grained methods in this weakly supervised setting rather than the strong supervised setting. Recognition methods in this research line also rely on unsupervised approaches to obtain semantic groups or semantic parts. And these groups can correspond to objects parts, fingering parts. So specifically, as shown in this slides, one of our work adapts the spatial pyramid strategy to generate part proposals from object proposals. Then by using the unsupervised clustering approach, we can generate part proposal prototype clusters and further select useful clusters to get discriminative part level features. And the rest unselected clusters, which might be the background or some other noises. Okay, on the other hand, the co-segmentation based method are also commonly used in the weakly supervised cases of fine-grained recognition. One approach is to use the co-segmentation to obtain object masks without supervisions. And then the Crosses et al. Propose heuristic strategies, that is a part constraints or part alignments to locate the fine-grained parts. Okay, now we can get the aligned fine-grained parts, so we can, based on these obtained parts, to get a whole objects representation as well as a global level image representation. Also, it is worth noting that the majority of previous work overlooks the internal semantic correlations among discriminative part level features. In more details, the aforementioned methods pick out the discriminative regions independently, okay? And they utilize these features in a direct way. So these methods almost neglect the fact that an object's features are mutually semantic correlated, and region groups can be more discriminative. So very recently, some methods attempted to jointly learn the interdependencies among part level features to obtain more universal and powerful fine-grained image representations. And some representative methods for capturing the interdependencies part level cues. Some methods use different feature fusion strategies, and these joint parts feature learning methods show significant higher recognition accuracy over the previous independent part feature learning methods. For instance, this is a work proposed by Lam et al. In 2017, and they proposed to sequentially uncover discriminative image parts and reasons over the entire research trace for recognition based on LSTM. As we all know, the LSTM can capture the sequential information. And constantly, the Ge et al. Also perform LSTM to fuse and encode the partial information of these complementary parts into a comprehensive feature in a bottom-up way. As shown in this pipeline, after the former two stage, and the first stage is weakly supervised instance detection and segmentation, and they use some advanced detection or saliency-based detection methods like CAM or mask RCN. And after that, we can obtain the object parts or object proposals. And in the second stage, they can generate some objects and also the part level proposals. And after this former, the former two stage in the third one, it employs LSTM on the obtained parts for context encoding. So the interdependencies of parts level features can be obtained. Moreover, in 2020, Wang et al. Developed a method based on graphs and to learn the correlation among these located parts. And some method like the graph convolutional neural network, and they can model the correlation between the nodes, and nodes in fine-grained recognition is corresponds to the parts, fine-grained parts. Also in IEEE 2020, Liu et al. Use knowledge distillation to fuse part level features and further enhance the region-based feature learning. It can get better supervision with object region constraints. And regarding the second aspect in the localizations, classification, and learning paradigms is to utilize the deep filters as a part detector. And we can use deep filters for localization and classification. In the deep convolutional neural networks, the deep filters, that is thin filters, they can refer to the learned weights of the convolution layers. And the responses from these deep filters can be viewed as localized descriptors. And these deep descriptors have the following properties, and someone like the locality, and that is means that they can describe and correspond to local image regions, and these local image regions can come from the whole input images. And the second is the spatiality, and they are also able to encode the spatial information. So as some work stated, exploring the use of CNN in our CV community, and researchers gradually discover the intermediate CNN output can be linked to the semantic parts of common objects. So in the fine-grained community, some researchers attempt to employ these filters outputs as a part detectors, and thus rely on them to conduct the localization classification, fine-grained recognition. Besides, one of the main advances here is that they do not require any part level annotations. So, for example, in the Xiao's work published in CVPR 2015, they performed a spectral clustering based methods on the deep filters to form groups. And these groups can serve as part detectors. So after obtaining these parts, and we can perform the rest process of the localization, classification, some network learning paradigms. And similarly, the NAC methods explores the channels of CNN as part detectors. And then by considering the geometry constraint, it can return the structural part level localization patterns for recognition. And in 2015, Liu et al. Developed a cross-layer pooling methods by aggregating the part-level deep descriptors using the activations from two successive convolution layer as a guidance. Okay, and then PDFS was proposed to select the deep filters corresponding to parts, and they then iteratively update the learned detector. Uh, it can result in the discovery of discriminative and consistent part level image regions. And another thing for this aforementioned method is that after obtaining the detected parts using deep filters from pre-trained classification TNNs, they typically uh, requires to train an offline classifier, for example, SVM or design trees, and then use parts-based feature vectors to conduct the final recognition task. So to facilitate the learning of both part detection and part-based classification in a unified end-to-end fashion, some trials want to develop an end-to-end trained fine-grained models. And one of the representative method was proposed by Wang et al. In 2018, and they utilized an additional learned 1x1 convolution filters at a small patch as a detector, as a part detector. And also it was followed by a global max pooling to keep the highest activations with respect to that filters for the final classification. And later, based on the end-to-end obtained the class response maps, S3N developed the leverage the class peak responses. And the class peak responses is local minimums at the basis of the part localization. And based on the class peak responses, similar to the aforementioned method, considering the interaction of part level features and S3N models part correlations in mutual part learning level. And as the third aspect, leveraging attention mechanism is proposed for handling a drawback of previous localization classification fine-grained methods. And that is in most applications, um, it might be hard to represent or even define common parts of some object classes. Let's say, for example, for some non-structured objects like food dishes or some flowers with repeating parts. And for these non-structured objects, we are very hardly to define the parts. So the definition of parts in these objects is difficult. So the attention mechanism can enable CNNs to attend to loosely defined regions for fine-grained objects, and as a result have emerged as a promising directions in the localization classification learning paradigms. And in the literature, Fu et al. And Zheng et al. Were the first to incorporate attention processing to improve the fine-grained recognition accuracies of CNNs. In concretely, ICNN, that is recurrent attention CNN uses a recurrent visual attention model to select a sequence of attention regions. And these attention regions can be corresponding to object parts. And ICNN is designed to iteratively generate region attention maps in a cost-to-fun fashion by taking previous predictions as a reference. So they can get the different or the zooming like part level fine-grained patterns. As a sister, the multiple attention CNN is equipped with a multiple attention module, and they can return multiple region attentions in a parallel fashion. Okay. Then in the after that, the Peng et al. Proposed multi-level attention models to obtain hierarchical attention information. The hierarchical information here means object and part level attentions. And the first stream is the object level, and we can, based on the object's attention, to capture the part level attentions. So it is a hierarchical information. Consequently, He et al. Also applied multiple attention to locate multiple discriminative regions simultaneously for each image via an pathway end-to-end discriminative localization network. And this localization network can simultaneously localizes the discriminative regions and encodes their features. And this multiple attention can result in diverse and complementary information compared to the aforementioned single level attention methods. Beyond that, the Zheng et al. Developed a trilinear attention sampling network to learn fine-grained details from hundreds of part proposals and efficiently distill the learned features into a single CNN. And the trilinear attention is also related to the higher order feature interactions in the rest portion of the tutorial. And also recently, G et al. Presented an attention-based convolutional binary neural net tree, which can incorporate attention mechanism with a tree structure to help to perform a cost-to-fine hierarchical fine-grained feature learning. And many other approaches in the localization classification paradigm have been also proposed for fine-grained recognition. For example, the STN or using the reinforcement learning, or some other machine learning techniques like low rank mechanism. And well, we will first introduce very famous spatial transformer network, and it was originally introduced to explicit perform spatial transformation in an end-to-end learnable way, and it can also be equipped with multiple transformers in parallel to conduct fine-grained recognition. And like the quantitative, the qualitative results show in this slides, and we can use two-stream or four-stream STN to capture the part level features. And each transformer in STN can correspond to a part detector with spatial transformation capabilities. especially for the non-rigid objects like birds. And for some other method using deep reinforcement learning, and He et al. Was the first to utilize deep reinforcement learning. In this work, it aims to capture both the object and part level to as a multi granularity discriminative localization and multi-scale representations using their tolerant reward functions. And inspired by low rank mechanism in machine learning field, and Wang et al. Proposed the DF GMM framework to alleviate the region diffusion problem in high-level feature maps for fine-grained part localization. And the method can select a discriminative region from the high-level feature maps by performing a low rank basis, and then applies spatial information of the low rank basis to reconstruct low rank feature maps. Okay, so these three are the representative some method for using some other techniques to perform the localization, classification, learning paradigms. And in these slides, I list the comparisons of qualitative results of these aforementioned methods. But due to the time limits, it's unable to expand in details. So interested audience can refer to our department survey paper. It is currently under review after the first round major revision. Okay, now let's move to the final section. Well, based on the observations in that table, we can summarize several conclusions about the localization classification subnetwork learning paradigms. And the first one is that the part level reasoning of fine-grained object categories can boost fine-grained recognition accuracy, especially for non-rigid objects like birds. Furthermore, the modeling the internal semantic interactions among the discriminative parts can also increase the accuracy of fine-grained recognition. So these types of research have attracted increased attention in recent years. And the second one is non-rigid fine-grained objects recognition, like the birds or dogs, is more challenging than rigid fine-grained objects like cars or aircraft. That's it to say the challenges might be partly due to the variations on object appearance or objects poses. And the third one is fine-grained image recognition performance can be improved by increasing the image resolution. And some results of fine-grained competitions also verify these observations. And the fourth one is there is a trade-off between recognition and localization ability for recognition by localization classification subnetworks paradigms. And it might impact a single integrate network's recognition accuracy. That is to say, such a trade-off is also reflected in practice when trying to achieve better recognition results. In our in training, it usually involves alternating optimization of these two subnetworks, or separately training the two networks followed by our joint tuning. So alternating or multi-stage strategies can complicate the tuning of the integrate network. So, and the last one is recognition by localization classification subnetwork based methods are challenging to apply when the fine-grained parts are not consistent across multi-categories. For example, for dealing with unnaturalist datasets, as mentioned by Serge, the unnaturalist dataset contain multiple meta categories. So the fine-grained parts should not be consistent across these multi-categories. So unified end-to-end feature encoding methods is more appropriate. And this learning paradigm will be introduced in the following portion of the tutorial. Okay, this is a first part of fine-grained recognition. And for more resources or references information, you can visit my webpage about fine-grained image analysis via the link. And I hope you enjoyed the talk and the rest portion of the